Okay, existence of limits. In these next few exercises, we are going to investigate whether a given limit exists or not. And in this fifth and sixth one, it's already stated that the limits do not exist. So we have to give reasons for why they do not exist. Okay, so let us start with the fifth one. In the fifth one, you can immediately see that this function x over absolute value of x is defined for every real number except x equal to 0, because if you put x equal to 0 here, then you get the form 0 over 0, which is undefined. But for other real numbers, that is for any non-zero real number, the quotient has a value. So let us see what that value is. We note that if x is positive, then x over absolute value of x is just simply x over x, which is equal to 1. And if x is negative, because that's what x will be, being non-zero, x can either be positive or negative, then this quotient has the value -1. So if we draw the graph of this function, say, then the graph will look like this. So this is our positive x direction, this is the positive y direction, and say this point is -1 and this point is say +1 on the y-axis. So when x is positive, that means when x lies to the right side of the origin, then the function value is constantly 1. So in that region, the graph is this line, this ray, and on the negative side, it is constantly -1. So as x approaches 0, that means as x is very close to 0, on the left side of 0, f of x is very close to -1, means actually it is constantly -1. But on the other hand, when x is very close to 0 but on the right side of 0, then f of x if I well, there is no f of x, but if you call this function f of x, then in that case f of x is very close to 1, and in fact it's actually equal to 1 in this case. So clearly, as x is very close to 0, the functional value is not approaching a single real number, so the limit does not exist. That is the reason. So we can write like this. In fact, if we are formally writing a solution, we should, before drawing the graph, we should write the following is the graph of the function whose limit we are investigating. Something like that has to be written, but I am not going to write that. I leave that to you. Now we proceed. What comes after this? Or if you want, you may not include the graph in the solution also. Clearly, this does not approach a fixed real number. Or instead of writing fixed, perhaps I should write single, a unique real number. A unique will be better. A unique real number as x approaches 0, that is, x is very close to 0. Hence, the limit does not exist. Although I just now said that you need not include the graph, but it's advisable to always include a figure, not necessarily a graph, whatever you are working with. If that somehow can be explained more clearly by a figure, then it should be included. That's just a general rule, even if for nothing, just for your own sake, because instead of saying these things, if you just look at the figure, you can immediately see that as your independent variable x is close to 0, the dependent variable is not approaching a single value. That can be seen at once from the figure. So that's why. Anyway, so let us now look at the sixth one. So the sixth one is this. Here, however, the figure is kind of necessary, because if we are not drawing the figure, then we have to take the help of a table of values in order to see what happens to this. Well, a table of values, but even if you want, if you really want, you can analyze this function also somewhat like this. If you do not want to use figures or numerical values in a table to see what happens to these functional values as x is very close to 1, you can just simply analytically write things down also, just like this one. But anyway, let's see what the figure is roughly. And that's why we are going to write in this case the following is the graph of the function. Let's call this function f of x, and let's now draw the graph. If you do not already know how the graph looks, then you have to in fact put some values, see what the points are, and then plot them and then join them. That is, you have to go through the process of drawing the graph actually. However, we know how this function looks roughly from our knowledge of graphs of this type of functions that we have already come across in a previous chapter. So the graph will roughly look like this. So this is our positive x, positive y on the left side, and this point is 1. That means this line is the line x equal to 1, because on this line every point has x coordinate equal to 1. So that is the equation of the line x equal to 1. Now to the left side of 1, the graph is like this, and to the right side of 1 it is like this, roughly. Now if you want to see y, you can see y just by looking at the function and without looking at any actual numerical value. Okay, so what is happening when x is less than 1? When x is less than 1, then x minus 1 is negative. So 1 over x minus 1 is also negative. That is why when x is less than 1, all the y values are lying below the x-axis. Now what about their magnitude? As x becomes somewhat far, it is somewhat far away from 1, then x minus 1 is numerically large. Okay, so 1 over x minus 1 will be numerically small. So that is the reason for this small y, negative y no doubt, but a small y. But as x gets closer and closer to 1 from the left side, x minus 1 being negative, that's fine, that is there, but we need not worry about negativity right now. Right now we are looking at the magnitude of x minus 1. As x gets closer and closer to 1, x minus 1 becomes smaller and smaller naturally, numerically, or distance wise. So its reciprocal gets larger and larger numerically, but because we are dealing with negative values, so it dips down, and the closer x gets to 1, the further it dips down and the faster it dips down. So the slope itself changes. You draw the tangent here, the point where you have your x, just below that point you will have a point on the graph, the point corresponding to this x, right? So here you can draw a tangent. The slope of the tangent will be the slope of the curve at that point, although we haven't really defined anything like that, but still just roughly saying. Now as you move your x closer to 1, then the corresponding point also will have a tangent. Now the tangent has a numerically larger slope, because it was not that steep. This is much steeper, and this steepness increases and increases faster and faster. So in the limit, actually this value does not approach anything. It in fact exceeds all real numbers numerically, or you can say it exceeds all negative real numbers in the limit. So it does not approach anything. Or if you want to say something vaguely, you can also say that this approaches minus infinity, although minus infinity is not a real number. Now the exact opposite thing in terms of sign happens to the right of 1. When x is lying here, then x is actually greater than 1. So x minus 1 is positive, and so its reciprocal is also positive. There is a but. So its reciprocal is also positive. So that's the reason for the graph being above the x-axis to the right side of 1. Now just like this one, here also when x is somewhat far away from 1, x minus 1 is large. Okay, without being too specific, just vaguely large. So 1 over x minus 1 is small, So that's why, that is the reason for this small y value. But as x gets closer and closer to 1, x minus 1 becomes small, so 1 over x minus 1 becomes larger and larger and larger. So it just grows without any bound. So here also, on this side also, when x approaches 1 over x minus 1 does not approach anything. It just exceeds everything. So that's why, unlike this case, here at least they approached different real numbers on either side of 0. However, here the function does not approach anything. So here also limit does not exist. So that's why we write there. The problem was in the previous one that the functional values did not approach a unique real number, but here the problem is in fact even more severe, that the functional values do not approach anything, since do not approach any real number on either side of 1, the limit of 1 over x minus 1 as x approaches 1 does not exist. That is the reason for its non-existence. Okay, so then that's the solution. Okay, now let's see the next one. For 5th and 6th one, I just simply wrote 5 and 6. No? So here also, let me just simply write 7. Suppose that a function f of x is defined for all real values of x except x equal to x0 or x0. Okay, can anything be said about the existence of a limit? About the existence of limit of f of x as x approaches x naught. Give reasons for your answer. Okay. Now this one is very general. Here f of x is some function some real valued function defined for all real values of x except this. That means the domain of this function is the set of real numbers from which the real number x0 has been removed. Now, can anything be said about the existence of this limit? Give reasons for your answer, and the answer is no. Nothing actually can be said conclusively about the existence of the limit. It depends entirely on the function. So that means, to show that, to support this statement that I have said just now, I have to provide two examples. In one of them, the limit will exist, and in the other, the limit will not exist. So that's why nothing can be said. And in both of them, the function will not be defined at some point, some real number. And to show that this in general is the case, I am not going to take a fixed value of x0. For me, for us, x0 is just x0. Okay. But the functions, of course, we have to define. So here is the solution. Consider the function in fact, let me just properly write the notation of function. From this domain into the set of real numbers, of course, a real valued function defined by okay, so now here is the definition. Say f of x is equal to, why am I writing it here? I can just simply write it here. No? F of x is equal to 1. That's it. Then the graph of f is the following. Is the following. Okay. Now here's the thing. Now while drawing the graph, we are not going to draw the y-axis. There is a reason for that. Since we have kept x0 an arbitrary real number, so we do not really know where x0 will lie on the y-axis, and on the x-axis, and in particular we will really not know the position of x0 with respect to the y-axis. So that's why we will not draw the y-axis. This will keep x0 arbitrary. That is, we will not, by drawing the y-axis and then deciding to draw the x0 either on this side or on that side, or maybe on the y-axis itself when it is 0, we will keep the arbitrariness of x0 intact. And in fact, to see what happens to the graph of the function, we really need not write y-axis. Need not draw y-axis. That's because the function is constant. So the graph will be like this. This is the point x0, the real number x0, and this is the point which is at a distance 1 from the x-axis or from the point x0. So the graph of our function will be this. x0 is not a point in the domain, so at x0 there is no value, we have no value, but elsewhere the function is constantly 1. So that's why a single point from this line has been removed. That's what this white circle indicates. But elsewhere we have the constant value 1, this distance. So that is the graph. So from the graph, and also just from looking at the function, the way it has been defined, it now becomes clear that in this case the limit exists and is equal to 1. Since f of x is constantly 1. Constantly 1 means constantly 1 everywhere. F of x, we can also say like this, approaches 1 as x approaches x0, or more precisely as x is very close to okay, that doesn't sound quite right. When x is very close to x0. Although this constancy of f of x is more precise because it's just simply 1, but still that also means that f of x approaches 1 as x gets close to x0. So the limit in this case exists and is equal to 1. So that is one example in which the limit exists. But now we will provide another example where the limit will not exist. So that makes the situation inconclusive, means in general you cannot see anything, you cannot say anything. Although in the problem there is only one function f, but we cannot give the same name to this next example, so we will change the name. Now consider the function g, again with this set as domain and its real value defined by the following formula. G of x is equal to 1 if x is greater than x0 and minus 1 if x is less than x0. So this is my function g. Then the graph of g is as follows. And we can use this figure itself by erasing this part, and x0 is still x0, but now we need a little more space below this figure. So roughly this much is again 1, the distance is 1, so this point is -1. Actually it's not -1, but it's x naught comma -1. So this is the graph of G. So again this situation is just like that first one, exercise 5, except in place of 0 here we have x naught. I think that one was 0, no? Yes. So since the reason will be similar for non-existence of limit, you can just simply see why in this case the limit does not exist. Since g of x does not approach a unique real number as x approaches x naught, this limit does not exist. So in general nothing can be said. Can anything be said about the existence of this? So in general nothing can be said about the existence of the given limit. So that's where the solution ends. Next, again another one similar but of course different. Suppose that a function f of x is defined for all, okay, defined for all x in the closed interval -1, 1. Okay. Now no longer is f defined on the entire real number. I mean, of course, here also it is not defined on the entire real number, but the situation is bounded here. The domain is bounded. Can anything, now in this case, can anything be said about the existence of this limit here the independent variable x is approaching 0. 0 is here a part of this domain. So if someone thinks that he can just use the unboundedness of those previous examples somehow, or maybe unboundedness plays a role in some example which can be used in the previous solution, because those examples I have only given. You may come up with some other example in which the fact that the function is unbounded plays a role. Here, however, the domain itself is bounded, and okay, that is not the only difference. The difference is that in this case the set is this, and at every point of the set the function is defined. In the previous one at x naught it was not defined. Okay, so that is mainly the difference. So then can it be something be said about the existence of this limit, and here the function is defined at 0 also. Again, give reasons. To support your answers, for your answer. Now here also we cannot say anything for sure. It will depend on the function itself. Consider the function f from -1, 1 into r defined by, well, let me deal with the easy case first, that the function is just simply 1. That's it. Here we do not have to be extra careful about not defining the function at some point, because it has to be defined at every point in this domain. So we define it to be constantly 1. Then clearly we do not even need to draw the graph of the function, but still if you want to see, I will draw the graph. Let me first write. Then clearly the limit of f of x as x approaches 0 is also 1. So here the graph is this. Again, positive y, positive x. But now we can have our thing only in this, within this strip. This point is -1 and this point is 1. And we have defined the function to be constantly 1. So this much is 1, and this is the graph. And because we are talking about a closed interval, so the boundary points also are parts of the graph. So you can clearly see that near 0, whether the point x is lying to the left of 0 or to the right of 0, the function is just constantly 1 throughout the interval. So that's why the limit is naturally 1. Next, consider the function g from, you can probably guess what I am going to write here next, from this to this, defined by the following formula. So I want the limit to not exist. That means I have to do something like this. So let me define the function g to be constantly 1 when x is non-negative, that is when x is either 0 or positive, it is not negative, but constantly -1 when x is negative. In this case, let's draw the graph first. Then the graph of g is the following. Is the okay, I won't have space to draw it there, so I have to draw it here on this side of this y-axis. Of the graph. Okay, so when x is 0 or positive, then the function is constantly 1. So this is the graph on this part, but on this part x cannot be 0. So this point is not a part of the graph. However, this point is a part of the graph, namely the point -1, -1. But okay, so why have we drawn the graph? To see that the limit does not exist. Why does it not exist? From the above graph, we can see that g of x does not approach a unique real number as x approaches 0. Or if you feel like not writing that, you can write in short that same thing like this also. That also means the same thing, as x tends to 0 or as x approaches 0, in symbols like this. And if you want to be more elaborative, of course you can do that by writing that on the left side it approaches -1, on the right side it approaches +1. So those things you can do, but the point here is that the limit does not exist. So does not exist. So nothing can in general be said about the existence of our limit, and that's the solution. Okay, the next line, if now here limit is given, if the limit of f of x is 5 as x approaches 1, that is given. Must f be defined at x equal to 1. If it is, must f of 1 be equal to 5? If it has to be defined, if it is defined at x equal to 1, must the value be 5 only? Can we conclude anything? About the values of f at x equal to 1? Explain. So for this one, non-existence of limit is not there in in the scene. The limit exists and is equal to 5, that is already given. So what we are concerned about here is the value of the function at x equal to 1. The first query is that whether it needs to be defined at x equal to 1 in order to have this. If it is, then must the value be equal to 5 itself? And in general, can we conclude anything about the value of f at x equal to 1 from just this limit? And the answer is no. Let's see how okay, so here nothing is said in general about the domain of definition of f. Okay, consider the function f from r minus 1 to r defined by f of x equal to 5. So from a similar function that we have already seen today, we can just simply say, then clearly limit of f of x as x approaches 1 is 5. So these questions really test our understanding of the limit notion. If we have some gap in our understanding, it will come out in trying to answer these questions. Do you remember while we were calculating limits in the previous video, and even before that we were discussing about limits, there I have made it abundantly clear by repeating it again and again that the limit of a function actually has nothing to do with the value of the function at that point where you are taking the independent variable, because the limit is not about what is happening at 1 but rather about what is happening around 1. Okay, so it does not really matter whether the function has this value or that value at 1, or in fact no value also, like this one. It does not matter. Still the limit can exist, and for this function it exists and it is equal to 5. Next. So the first one has been answered. Must f be defined at x equal to 1? No. In fact, without having any value of f at 1 also we can have the limit 5. Next, consider the, this creates a very peculiar problem, because only f has been, this function has been given f, the name f, but if it's general we need to change f. So what should I do? Just for this solution, or maybe the next one also, I don't know, let me call the next one also f, because specifically this is given. No? I cannot write g. Consider the, if I want I can write, but still forget about this f. Next, consider the function f from r into r defined by, okay, so here what, how do I need to define this? Oh, okay, fine. So this is how I am going to define the next f. I am treating this f as different from the previous one. This is 5 if x is not equal to 1 and 0 if x is equal to 1. Then that means that 1 f of x has the value 0, but elsewhere it is constantly 5. So it is that situation where you had generally x naught, although at that x naught there was no value, but here the value is 0, but elsewhere it is 5. So on the left of 1 also it is 5, and on the right of 1 also it is constantly 5. So clearly here the limit exists and is again 5, but the value we have defined of the function at x equal to 1 is 0 and not 5. It is 0 but not 5. So this is also not necessary, and this is not a consequence of this. Clearly, or let me write it there. Although f of 1 is not equal to 5. And finally, can we conclude anything about the value of f at x equal to 1? So we just need our hypothesis to be true, which is that the limit of the function at x equal to 1 is 5. But that does not say anything about the value of the function at x equal to 1 when we have a value. Here we do not have a value, but here we have the value 0. You can just simply see that if you change this value to something else, then also the limit exists and is 5. Finally, consider the function f again defined from R into R, defined by this a similar formula, but now it will be arbitrary. Where C is an arbitrary but fixed real number. Then for this function also, despite it having the general value C here, still the limit exists and is 5. So that means we cannot determine what C is, or in fact C is not uniquely determined, and let alone uniqueness. It can be anything. It can be 5 also, or something else. Note that C does not affect the above limit, or in other words, the above limit which is given does not determine C. I think it will be better to write that, but anyway, this is the solution. And finally, let's see the 10th one. If f of 1 is equal to 5, okay, sorry, okay, from so many different angles the authors are approaching the same thing. Here the value of f at 1 is given and it is 5. Must the limit exist? That is the first question. And then if it does, must the limit be equal to 5? And again, can we conclude anything about the limit in general? explain. Here also you can guess that we actually cannot conclude anything general about the limit. It may exist, it may not exist, and even when it exists, it actually need not be 5. It can in fact be anything. Now, this solution I am not going to write formally, I will just give you the idea because we have already seen quite a few like this. So now f of 1 must be equal to 5. The first one is this question whether the limit exists, and the answer is no. To see how you consider this function, so the graph of this function will be this. We in fact do not need to go below the x-axis. So let me just draw this much y-axis only. Say this point is 1 and somewhat above that we have 5. So what the definition says is that when x is less than 1, then, and we also need a 1 here because that's the point where we are considering the limit. So when x is less than 1, then the functional value is constantly 1. And when x is greater than or equal to 1, then the functional value is constantly 5. Okay, so this is 1 and this point is 5. So you can see that the function at the point 1 has the value 5. So f of 1 is 5, that is satisfied. But the limit does not exist because as your this one is also one that I need to mention. As x approaches 1 from the left, f of x is constantly 1, whereas as x approaches 1 from the right, it is constantly 5. So it does not approach a unique real number as x approaches 1, the f values. So the limit does not exist. Then what? If it does exist, must it be 5? No, that is also not true. And the function that shows that is this. Say I define the function to be constantly 1 when x is not equal to 1 and has the value 5 when x is equal to 1. So for this one, the graph will look like this. Again 1, 1 and 5. Okay. Now when x is not 1, then, and this is also of course 1, the function has the constant value 1. So when x is either on this side of 1 or on that side, the functional value is constantly 1. Okay, I think I went a little inside. You understand, okay, it does not reach this point. But when x is 1, then the functional value is 5. So the graph of this function has this one broken line, it has 2 parts, and this single point. Now here the limit exists, you can clearly see near 1 the function is 1, constantly 1. So the limit exists and its value is 1 and not 5, although the functional value at 1 is equal to 5. So here the limit exists and is 1. Now can we conclude anything about this? Of course we cannot conclude, we can conclude absolutely nothing about this just from this condition. The limit may not exist at all, which we see here, but the limit also may exist, and even when it does exist the value need not be 5, and if you just in place of taking 1 you take any real number other than 5, you see that the similar function gives you the limit equal to that real number. So it can be anything, it can be made to exist and its value can be made anything, it can be made to not exist also. So nothing can be concluded about the function just from its value at 1, which is 5. So that's how you can arrange the solution and write it formally. So here the solution ends, and let's end the video also here. In the next few exercises, in this set of exercises, we have to use graphing calculators and numerical or ordinary calculators. So those I will leave to you, but they are very important, because by going through those exercises and creating a solution, going through those tables, seeing what the graphing calculator is giving you, analyzing those figures will make your understanding of this notion of limit even more solid and in fact even more clear. So what we are going to do next is that we will then take up the exercises that come after that, after those numerical and graphing exercises. So we will get to that in the next calculus update. And tomorrow is of course Saturday. So because we have the last Saturday we solved Lee's algebra problems. So tomorrow let us solve Galilean's group theory problems. Then on next Saturday we are going to again solve Galilean's ring theory problems. So with that I wrap things up. So see you tomorrow with Galilean's group theory exercises. Until then, this is me, Lucifer from A Mathematical Truth. Have a nice night.